So here we are, new topic, new location. This is our glamorous library home office at my house since we're banished from campus. If you're lucky, you may see the dog wander in and out of the frame behind me. If you hear some noise in the background, it's probably my 8-year-old watching Nickelodeon in the other room. This is life in pandemic. So. At the end of the last lecture, we talked about how we know that light has wave nature. And this is something that was demonstrated in the early 1800s thanks to the work of people like Thomas Young doing interference experiments, Augustin Fresnel, and Francois Arago showing that light interferes like a wave, and that conclusively proves by the early 1800s to pretty much everybody who cared that light is a wave, that different colors correspond to different wavelengths of light, and we can see that in the diffraction patterns that they make when you send light through a double slit or through a diffraction grating, a device that we'll talk about later. And these discoveries convince pretty much everybody that light is a wave. Middle part of the 1800s, James Clerk Maxwell comes up with a unified theory of electricity and magnetism, combining those two phenomena. One of the predictions of that theory is that there should be electromagnetic waves. There should be a combination of an electric field oscillating in one direction, a magnetic field oscillating in the other direction, and those should sort of sustain each other as they go along through space, and they travel at the speed of light. This is a prediction that light is an electromagnetic wave. And this is later confirmed by Heinrich Hertz in a set of experiments we'll talk about in the next lecture. So by the late 1800s, everybody is absolutely convinced that light is a wave. It's an electromagnetic wave traveling along through space, and that this is the basis for understanding all phenomena involving light. And so people are running around looking at, what can we learn by looking at the light from different objects, and what sort of physics models can we come up with? And this turns out to break absolutely everything. And the place where that break starts, the place where quantum physics gets launched, is surprisingly simple. It's right here. This is the toaster oven that we used to have in our kitchen. And if you look at those heating elements, that red glow is a very simple and universal phenomenon that's very recognizable. You take a piece of metal, you heat it up. As it gets hot, it starts to glow, first red, then yellow, then white, and so on. The amount of light that it emits increases as the temperature increases, and the color changes. If you look at the spectrum of the light, you take the light and split it up into its component wavelengths and ask how much light is there in a narrow band around any given wavelength. What you see is a very simple phenomenon. There's a broad peak on a graph like this that moves to shorter wavelengths as the temperature goes higher, and that the total height of the peak increases, meaning it emits more light altogether. This is a very simple, very universal behavior. It doesn't matter what material you have. If you can get it hot enough, it will glow with exactly the same color. The only thing that determines the color of the light emitted by a hot object is the temperature. This kind of really simple, really universal behavior is like catnip to theoretical physicists. So people started making all kinds of models about, trying to connect this to basic physics principles and understand how this worked out in terms of light as a wave. All of them failed. The guy who eventually cracked it is this fellow here named Max Planck, who clearly went a little crazy in the process. He was a German theoretical physicist, and he had first come up with an empirical formula that describes the shape of that peak in the spectrum of a hot object like the filament in that incandescent bulb. Planck's formula works really well, but he had no way to understand it in terms of basic physics principles. So he was trying to do that, and he kept failing. Eventually, he found a way to connect it to basic fundamental physics, but in doing that, he had to make a radical break with the physics that everybody understood, that light is a wave. Now, in order to explain what Planck did and why it works, I first have to explain the wrong way of doing this. So I'm going to go through in some detail the incorrect approach before we come around to the correct one. But the basic idea starts with a very simple principle. The idea is to come up with a model of a hot object that's based on this fact that the radiation emitted by hot objects is universal. It doesn't matter what the thing is made of. So Planck had a simple model for this. This is actually what people doing spectroscopy in these situations use. The theoretical ideal is referred to as a black body. That means it absorbs any light that falls on it. Physical model of this is a box with a tiny hole in one side. And what that does is that gives you something that effectively absorbs all of the light that comes in, because any light that goes in through the hole, provided it's small enough, is going to bounce around many, many times inside the box before it could possibly find its way back out. Right? This is essentially the same principle as these like stupid little destroy the blocks cell phone games that I play to pass time. Right? You get a little narrow opening, you get some balls up in there, they bounce around forever, and then clear all the bricks. And I've done hundreds and hundreds of these levels because I have competitive OCD. Anyway, this is the model that Planck was using, and the idea is to take that box with a hole in it and figure out what kinds of waves can exist inside that box, right? And then assign each of those waves an equal share of the energy that's available due to the heat of that hot object, right? And if you do that, the hope is that the little bit of light that leaks out, right, is something that reproduces a blackbody spectrum. Right, the light that leaks out has nothing to do with the light that comes in, because the light that comes in is bounced around so many times it's been absorbed. The light that leaks out has to do with what can be sustained inside the box. So you figure out what's inside the box, right? Insert Brad Pitt quote here. Figure out what's inside the box, and you find the spectrum of frequencies and wavelengths of light that are allowed to exist. Now, this might not sound like a big simplification, but this is actually a problem that physicists know how to solve very well, because it's what's going on in a musical instrument like a pipe organ or a guitar string or any kind of vibrating musical thing. Right. In those systems, what you have, a pipe organ is an excellent example because it's essentially a big tube with a little hole in it to let some sound out. Inside that tube, at the ends of that tube, the wave has to stop, right? Which means that the only waves that will happily exist inside there are ones with a particular wavelength. The longest of those wavelengths is twice the length of the tube. You get half a wave going across from left to right, and then the other half coming back, right? And this is a wave that is called a standing wave. The two ends are fixed, and it oscillates in the middle area. That has a particular wavelength that depends on the length of the pipe, and that's why you have all of these different pipes in a pipe organ, because each one has a different fundamental tone. But of course, a real pipe organ isn't just a single frequency, it has lots of overtones, and those overtones are also standing wave modes of the waves inside the pipe. So the next one would put a full wavelength of the wave inside the pipe. It goes up, it goes down, and back to zero. Right, and that has a wavelength that's equal to the length of the pipe. Then there's another one that has 3 lumps in it, right? It's a wave and a half across it that has a wavelength of 2/3 the length of the pipe. The next one is half the length of the pipe, and so on. You get many, many of these modes inside the organ pipe, and that's what determines the sounds that come out. Right, the fundamental mode is the loudest and strongest, and that's the main note that you hear, and all of those higher frequency overtones give you sort of the rich tone of an actual pipe organ, as opposed to like simulating a sine wave on a computer. So Planck's idea was to just count up all of the modes that you can fit inside a pipe of some length, and give each one of those an equal share of the thermal energy that's available due to the heat in the hot object. So if you do that, what you can do is you can sort of count up how many modes are there in a narrow range of wavelength, and sort of mush them together, and then just say, well, in that range of wavelength, we expect an amount of light to be emitted that's equal to the number times however much radiation each one puts out. When you do that, you get a curve that looks like this. This is not a blackbody spectrum. This is something that just blows up at very short wavelengths. The reason for this is that these wavelengths that are allowed get closer and closer together as you go to shorter and shorter wavelengths. So there's more modes within a given range, and it just runs away. It predicts that you should have an infinite amount of energy being emitted at very, very short wavelengths. That's clearly not what happens in a toaster. wouldn't be very useful as a toaster either. If my toaster, every time I turned it on, just sprayed out an infinite amount of ultraviolet and X-ray radiation, right? Not so useful. This is a very serious problem for physics. It eventually picks up a colorful name. It's called the ultraviolet catastrophe, which would be a fabulous name for a band. And this is really due to the work a little bit after Max Planck by Rayleigh and Jeans, that they articulated this in a way that most clearly leads to the ultraviolet catastrophe. But Planck was hitting the same problem with a slightly different approach. So how do you fix this? All right, so Planck managed to find a solution, but he was never super happy with it because it required a radical break. Right. The issue is that this tiny leak of light coming out can't be the full story, because if you just tally up all the modes that can exist inside the box, you say there should be an infinite number of short wavelength ones, and that just doesn't work. Right. So how do you fix this? Well, Planck went back to the source of the radiation, and he said, look, I don't know what they are, but there's something in the walls of the box that's oscillating to produce light. Right? It's producing a wave. It must be oscillating at some frequency. And I'm going to say that each of those oscillators has a characteristic energy. That energy is equal to some number multiplied by the frequency. So if I double the frequency of the light, then the characteristic frequency of the oscillator that emits it has to double. Okay. Now the next thing that Planck did is the radical step. He said that we're going to say that only integer multiples of that characteristic energy can be emitted by any given oscillator, right? So I can emit 1 unit of energy, 2 units of energy, 3 units of energy, but I can never emit 1.5 units of energy. I can't emit pi units of energy, only integer multiples of that characteristic energy. Right. This is a really weird thing. Planck, when he did this, thought he was just pulling a trick that you use in calculus a lot, where you set up something as a sort of discrete arbitrary sum, and then you turn it into an integral, and you do a bunch of math, and everything works out. And he thought that at the end of the day, he was going to be able to take a limit as this number that converts from frequency to energy went to 0, and everything was going to go back to being smooth and continuous and happy. But it didn't work. Works brilliantly, though, if you keep that characteristic energy and that requirement that only integer multiples are allowed. Let me explain how that works. So let's go back to our picture of these standing wave modes inside the box, and then say each of these is going to be allotted an equal share of energy that will represent by the little blue bars there. That's the share of energy that's assigned to each mode. It gets to emit that much energy worth of light. Well, for a very long wavelength, a long wavelength corresponds to a low frequency. That low frequency has a low characteristic energy, so that share of energy that it's getting is a lot of light being emitted, a lot of units of that characteristic energy, say 6 of them. Okay. When we go to the next mode that's allowed, right, that has half the wavelength, then it's going to be, well, it's twice the frequency, that's twice the characteristic energy, which means that the same amount of energy is half as many quanta, right? Half as many of these units, so 3. One after that is 1.5 times the fundamental wavelength, right? That's 2 quanta worth of energy. The one after that ought to be 1.5. Okay, but we're not allowed to do 1.5. We can only do integer numbers, right? We can only do 1 or 2. Right? We don't have enough energy to make 2, which means we can only do 1. The amount of energy at this 4th mode, right, the amount of energy that it gets to emit is smaller than the energy that it should have been allotted. Right? And if you keep on doing this, eventually you get to a point where the characteristic energy is just bigger than the share of energy allotted to that mode, which means that it can't emit any light at all. Right? This is a radical solution that fixes the problem of the ultraviolet catastrophe. It says that the amount of light that you see emitted at very, very short wavelengths, at very high frequencies, is crushed by this requirement that you can only emit integer multiples of some characteristic energy. When you do that, then you can use this feature to derive the formula that Planck had already found empirically, and prove that science works in the terms of this famous XKCD cartoon. Or if you would like something a little, less profane, here's some actual data showing the measurements of the cosmic microwave background radiation from an orbiting satellite. And the black points are data showing the radiation that's left over from the Big Bang that looks exactly like a black body, and that red line that goes through every single one of the points is the prediction of Planck's formula. So Planck's formula and this derivation is a smashing success, makes him an extremely admired and powerful person in Germany. There's now a whole set of national laboratories named after him, the Max Planck Institutes in Germany. Sets him up for life. He was never really happy with this idea, though. Right? He always thought that this integer multiple characteristic energy business, this seemed like a really ugly mathematical trick. It's something that he wasn't happy that he had to do. And he always hoped that somebody else would come along and find a more elegant way to get to the same point, to arrive at the formula without having to do this ugly mathematical trick of these discrete emission and energy. That just bothered him his whole life. Unfortunately for Planck, it turns out that that is exactly the right thing to do. And what did happen is in 1905, everybody's favorite patent clerk came along, picked up this idea and ran with it and fully established quantum mechanics as the theory of light, and was the first to really state that light should have a particle nature. But that's a topic for another lecture. We'll come back to that and the experiments that led Einstein to make that prediction next time. So there will be a quiz on Nexus for you to answer some simple questions about this lecture. Make sure you're paying attention. And then there will be another video setting up the experiment that we're going to talk about and setting up what you need to do to do the activity that will hopefully lead you to the same conclusion that Einstein reached, which is that despite what everybody thought in the 1800s, light actually has particle nature as well. So we'll come back to that next time. Until then, good luck.